Okay, good afternoon. I'm Silvia Rota, and I'm here to present my research about keyword search over relational databases. And I'm going to present an approach that is based on hidden Markov models. My tutor for this research is Professor Sonia Bergamaschi, and the co-tutor is Francesco Guerra. Okay, as an overview of what I'm going to present, I'm going to start with a motivation of my work, followed by an explanation of how keyword search on databases works, and a small overview of what existing techniques do and what are my contributions. And then I will go through the details of the approaches that have been developed based on hidden Markov models. And at the end, it will be a small resume of a tool that has been implemented with these approaches, and some more overview of the experimental evaluation. Okay, first of all, let's start with the motivation. So what is keyword-based search? We all do know what it is since we use it every day on the web. It's like nowadays is the de facto standard for web search engines. So it's very utilized and well known. And it has advantages that regard the user-friendly interface. It's very easy to understand by any type of user. Anyone can use keyword search and can understand it very quickly how it works. So this is the main advantage. The disadvantage is the low expressivity of keyword queries. Keyword queries are intrinsically ambiguous because they are basically extracted from natural language. There are some sort of resume of natural language query, and the semantics can be ambiguous. So as a result, what is going on? Okay. As a result, the results obtained from keyword query search are imprecise, and there is need to find ranking algorithms to sort the results, as it happens in normal web search engines. What is the difference? So between a search on the web and a search on structured data sources. On structured data sources, we usually employ a structured query language. This language requires expert user that knows both the query language and knows the scheme of the data, I mean the structure of the data in the source. And they have advantages which are the high expressivity and precision. The queries are logical predicates, and the results returned is a Boolean result. A result either respect the logical predicates and is returned, or is not returned. So there is something, it changes alone. I'm not doing anything.
Because it was a function, it was activated when you break.
Okay.
Because you are coming.
Okay, so there. And so as you can see, there is a very big difference between the two different types of queries. And what can we do if we enable keyword search on databases? We can substitute, for instance, the SQL queries. And in this way, we can allow a fast and easy access to the content of a database for non-expert users, which nowadays is very difficult for a non-expert user to query a database without knowing how to query it. What they do actually to allow non-expert users nowadays to query the database is create form interfaces. And the problem is that the database designer has to predict all the possible query needs of the users and create forms for these queries, because each form corresponds to a predefined query. So either we have a big effort of work from the design point of view, and on the other side, we have users who need to choose from different forms before even being able to pose a query. So forms can be substituted with a simple keyword query interface. And where can we apply this? We can apply this in business databases, where employees could be able to query the database without any issue. We can apply this to mediator systems, because in mediator system we have a global schema that can be queried to address, and the query will be transformed into queries over data sources. But since the mediator schema is integrated from many different schemas, it could be potentially very large and difficult to understand. So we will avoid the problem of being able to understand the global schema. And also it could be have application, important application to query on the web, because actually the information that is indexed and accessible, accessible by the search engine is only like a fraction of the information present on the web. A lot of information resides on online databases that are not indexed by the current search engine, so they cannot be researched. So it would be nice to enhance the answers of the current search engines with answers extracted from those databases online. So the potential for keyword search in databases are big, and let's now see what are the differences and the steps necessary to make keyword search in databases. First of all, it requires different techniques compared to traditional keyword search on textual documents and on the web that are hypertext documents. There are some offline steps, and first of all, the data is modeled in a graph, and the graphs represent is the tables, attributes, the domains, basically all the structure of the source, and then the data content of the database is indexed in order to find the queries. And there are many different techniques to build an index of the database. I will not go in details. And then after this offline phase, at query time, we have other phases. We have the first step is to process the keyword queries, like simply cleaning the queries. This is a very standard process that is done also by normal search engines. Keyword queries can contain words that are called stop words because they not carry any useful semantic, and there can be typos of any kind of errors, or those need to be removed before doing anything else. And after that step, the keywords need to be matched against the terms inside the database. In this phase, the indexes that were built before are used to identify where are the keywords inside the database and to find them very easily. After that, we have basically the location of the keywords in the database, but the keywords may be located in very different parts of the database, like different tables. And so to form an answer, those tables need to be joined, and there are many possible joining paths for the same matches. So the next step is to identify these joining paths using the graph built before, and to rank them appropriately using some score function. Usually, the score functions are very different, but usually they use a TF, IDF measure taken from the information retrieval field, or they score based on the size of the subgraph that contains the joining path. Other steps are, after the previous one, are the query execution on the database. Once the joining path has been identified, a query in SQL can be formed, and it can be used to query the database. And of course, the top answers will need to be presented to the users. Since the answer can be potentially huge, imagine to query a large database with a query that returns many results. So some researchers have focused on techniques to better represent the results, which, for example, with clustering, or use it like snippets, or any kind of visual tool. Okay, so what is the situation in the state of the art? The situation is what they studied techniques to do the steps that I just illustrated, and mainly they heavily rely on indexes built on the database content to find the keywords. This is a very important step, and this gives a very precise way to find the keywords, but at many disadvantages, because it's hard to manage a database if the database is subject to frequent updates. Or this technique is taken from information retrieval. Treat the keywords and the database content as just a set of words without any, the semantic contained in the structure of the database and in the sequencing ordering of the keywords in the query is completely lost. And this is quite annoying. Okay.
The timer of it.
Okay. So, also to build an index, an important point.
Wait a minute, that he's changing the time. Ma perché? Ma non ci vuole il
Because no, it was activated during the break to show cyclically
The professor of multimedia systems. No, the multimedia interfaces.
Okay. Thank you.
Thank you.
Marco,
Okay. So, the state-of-the-art techniques, in order to build an index, they make the assumption that the database content is available a priori. This assumption is valid in some contexts and not in others. Like, for instance, it's valid if you are providing keyword search for an internal database in a business, because the business owns the database and has access to the content. But it's not possible to access the content in many other cases, like in databases present in the deep web, because they provide only a query form as interface. I mean, a form, like some kind of form interface to access the content, or they cannot be applied to databases of third party for any possible reason, or even in mediator system, because mediator systems are transparent. You cannot access the content of the data sources. So, to cope with this issue, we developed new approaches that, by hypothesis, they assume that the database content is not available a priori. So, if when the issue is the indexes process, the solution is let's avoid to build an index on the database. So, our approach starts from this assumption: we cannot build an index on the database. So, our approach becomes viable in all cases that were not viable in the previous approaches. But on the other side, we cannot anymore match keywords exactly to the database term, because we have no idea where the keywords are inside the database without an index. So the approaches that I illustrated before of keywords to database mapping, that was basically straightforward for other approaches, just use an index and localize them. Here it becomes something more complicated. It becomes some probabilistic function, because we don't know exactly where the keywords are. So we start from the hypothesis that only the schema of the data or a metadata describing it is available. And we use a probabilistic model to model the location of the keywords inside the database, because this is the main focus of the research, this approach, since it's so different from the other approaches. So, and since it's a probabilistic matches, we try to use as much semantics as we can extract from both the database structure and the ordering of the query. That is something that other approaches usually do not exploit much. Okay, so given a database schema and a query, the goal is to find a mapping between the keywords and the database elements, where a database element can be any of the following. A keyword can map to a table name, can map to an attribute, or can map to any value inside the attributes. And we call all these possible mappings the database vocabulary. And as you may notice, this is, I wrote an example. Keywords may have different meaning, and it's important to disambiguate the meaning. And the other keywords in the keyword query needs to be taken into account in order to disambiguate, because otherwise we have no way to distinguish, because there are no indexes. So the context is very important to disambiguate the semantics. Okay, so in this approach, in order to model this matching, we use a hidden Markov model. Why the Markov model? Because we've been studied other models also, but this has been, this looks like the most promising, both because of the accuracy of the model in the results and of the performance. I mean, time performance. Because when we pose a keyword query, the user expects to have a result returned in a fraction of a second, and that is important. We cannot use a probabilistic model that takes 1 hour to compute the result. So here is a brief description of the Markov models. They are generative. So they are composed by observation and states. The observations are believed to be generated by the states. And they are parametric models. They have many parameters here wrote by a resume of the parameters of the model, basically. And this is a graph of ideal Markov model. If you want to design, to draw it in a graphical form, there are states that are connected by links that are called transitions, and there are emissions. Each state has observations that are emitted from the states. Basically, the model represents a situation in which an observer can observe a sequence of observations written in blue, and the observations are believed to depend on some hidden states that act behind the model and are not clearly visible. So what we can do with an hidden Markov model? Usually, the hidden Markov model are used to address 3 problems. We address 2 problems that are related to our contest and that are a bit different from the original problems. We need to find the problems of interest are prediction. We want to use this model to predict the top case sequence of states that best matches a given sequence of observations. And on the other side, we want to maximize the model performances, so we need to use training to optimize the model parameters. So how do we apply the hidden Markov model to in our context? In our context, we use basically the state of the model to represent the structure of the database, and the observation to represent the possible keywords. So the parameters have a meaning in our context. And how do we estimate the parameters? In the first approach developed, we estimated the parameters with heuristics. And to estimate the initial probabilities, we use an algorithm that is called its algorithm, and I will explain soon. And to set the other probabilities, we use empirical rules and similarity measures. So let's start from an example of what is the model. This is a very simplified version of what happens in our model. This is a database table on the top, and the relative hidden Markov model derived from it. But this is a very simplified version of the thing, actually. So, where the observation sequences can be keyword queries, and there is an example below. So basically, as you see, the states represents elements of the table, and the observation, which are like, in this case, are elements that can appear in keyword queries. So how do we estimate the initial probabilities? Initial probabilities in the model are the probabilities that the first observation in the sequence correspond to a certain state. It's basically the initial probability tell us from which stage to begin the search. To estimate this probability, we use this algorithm. This algorithm is being employed for link analysis is something similar to the page rank. It basically scores nodes in a graph and gives 2 different types of scores. We use only the authority one. Basically, a node in a graph has a good authority scores if it contains information, if it's a good information content. And we use a special database graph to calculate these probabilities, which is a graph in which the nodes are the table in that database, and the links are the foreign keys. And what we calculate is the authority of tables. What are the most important tables inside the database? And also we use a modified version on the algorithm where the weights, we use weighted edges. The weight is given by the informative attributes, which are the attributes that are not links. Foreign keys are considered links to other tables. Okay, so let's estimate the other parameters of the model. We have transition probabilities. Transition probabilities is the probability to change from one state of the other in the model, inside the hidden Markov model. We use heuristics. These heuristics are basically taken from common sense, and they can be resumed by the following two common sense rules, we can say that in each table there is one attribute more popular than the others when searching information. For example, the attribute name is more important than others when searching information about persons. It's a very simple example. If you want to find an information about a person, you don't search the person by his address, but you put his name. So this is very common sense of what people usually do. And also another common sense is that humans tend to write queries in which related keywords are close to each other. And the same applies to who designed databases. If tables that contain similar information are linked to each other. So it is more likely to have a transition to elements inside the same table than transition to elements in different tables, and so on. I mean, it's more likely to have transition between elements in tables connected to foreign key than transition between tables not connected. So following these two considerations, a lot of heuristic rules have been developed to set the parameters. Moreover, other parameters of the model that needs to be estimated are the observation probability. Observation probability are the probability that being in a certain state we observe some observation, which in our context mean what is the probability of being, having a certain keyword associated with some database term. And to do this we use similarity measure for the schema element, because if a keyword has to be mapped into a schema element, we just need similarity. Or you can also use synonyms. Imagine we have like a database containing information about hotels, and the user writes hotels in Modena. Hotel can be the name of a table in this case, and can be mapped into a schema element then. And also we have domain elements, which are the same, for example, in this query Modena. Modena is not present in any schema, and is part of the content, which we do not index. So to try to at least distinguish where the keywords can be, we use regular expression to exclude certain fields, like for sure Modena cannot be a phone number. And this helps in disambiguating. Okay. So after we modeled with the hidden Markov model, we use the hidden Markov model to find the best mapping between the keywords and the element. How do we do this? We use the list Viterbi algorithm, that is an extension of the well-known Viterbi algorithm, to find the top K structural query that best match our keyword query. And in a second approach that we developed a novel algorithm based on the list Viterbi algorithm that we use for training. Basically, we took the expectation maximization procedure that is a training algorithm, and in the expectation step, we use the list Viterbi training algorithm to calculate the expectation. The maximization step is basically a step where the parameters of the model are maximized to cope with the expectation calculated in the previous step. So this list Viterbi training algorithm that we developed is able to use the user feedback when present, or simply use a query log when the feedback is not present, which means the algorithm is semi-supervised. It can be used also completely in a supervised or unsupervised manner. And also we developed both the batch and online version, so the algorithm can actually be used in an incremental version online. So this means that there is no pre-processing offline. The system can start to work immediately, and the performance is improved during time, because every time that a user type a keyword and return a result, this is used to train the algorithm, both if there is in case of feedback or in the case there is no feedback. Okay. How does this algorithm work? This is some details about the algorithm, even if didn't put any formula. The algorithm is a dynamic programming procedure, and it has some assumptions that are here written, and the assumptions are all respected in a first order hidden Markov model. That is exactly what we use to model the problem. So we can apply this algorithm. So this is what I said before. The algorithm works in 2 steps. We have an expectation step in which the top k-state sequences that are the best, with the ones with the highest probability of matching a keyword query are computed. And in the maximization step, the model parameters are adjusted to maximize a log likelihood function that takes into account, since we use this function in the expectation, we take into account only the top k best sequences. Okay. So the main characteristic, I told them before, I don't know why these slides. Repeat them. And, okay. So both approaches, the one using a hidden Markov model with heuristics and the one using a hidden Markov model where the parameters are optimized with a training procedure, have been implemented into a prototype search engine called Kiri. And this search engine has a user-friendly interface for keyword search, like Google Type. The keyword search steps are shown to the users. I mean, all the steps of the process, what happens is shown, because this tool has a demonstrative purpose. And also, this tool has been used to evaluate the performances of the approaches on different databases. So it has also been used to evaluation. And moreover, we have tried what is the various effect of different levels of feedback from the users on the system. This is an overview of the tool, of the architecture. On the left, there is a user that poses a query. The query is parsed for cleaning and is analyzed by the hidden Markov model matcher that finds the match with the terms in the database in a probabilistic way. Then, of course, we have a metadata repository that log what is going on. The query is then passed to a query generator that finds the join path and build a SQL query, which is then passed to a wrapper that communicates with the database. The results is also returned by the wrapper directly to the user. So this is how it works in detail. The part that I explained before about the hidden Markov model process regards only the part in red with the hidden Markov model matcher. This is an overview of the evaluation that has been done. We have tried the system in various databases. And we can here see the comparison between the hidden Markov model with the heuristics and the hidden Markov model after training. And this is accuracy on the top k results. It's something similar that you can find also in information retrieval. It means, in this case, we measured only basically how many times we assume that the correct result is only 1. And we see how many times the correct result is the top 1. Or top 5 or top 10, depends on, there are, like this case is in the hidden Markov model with heuristics, the correct results appear in top 1. This is different databases. Sometimes in 40%, sometimes it's over 60% of the cases, and appear in top 5. Top 5, the maximum is 80%. Well, actually, what is important in this kind of search engines is that the correct results usually appear in the first result, usually is considered the top 10 results. And you can see in the top 10 results, the accuracy is already good. On the other side, we have the hidden Markov model after training, and the performances that these keys are completely different. As you can see, after training, the model is customized for that specific database. And you can find that the results is basically quite always present in the top 10, and which means that it's very, very good system. If we can find the correct result, basically quite always. And the probability of finding the result on the top 1 is around, is between 80 and 95%, so it's very good. These are time performances, which, as I said before, are very important for applicative purposes. So here is a comparison, and on the first graph you have the case of with one keyword, while on the other case we start with 2 keywords. But because of course the time of answer depends also on the number of keywords that the user put in. So as you can see, this is milliseconds. So in most of the cases, the time is less than 1 second, and overall less than 10 seconds also in some cases, in some databases, depends on the situation. But generally, it's a matter of seconds. It's not a matter of waiting minutes or like 20 minutes or something like this. As it happens in other approaches, there is a much more longer time to wait. Okay, finally, this is only for the trainings. We measure how fast the algorithm can learn. This is the learning curve. We measure how much iteration it requires in the interactive version to achieve good performances. And as you see, the curve can be very steep. These we represented many different conditions, like depending on how much feedback we provide at the beginning and how much feedback is present after some iterations. And basically, the performance stabilizes after a very low number of queries. Let's say that after 250 queries, the system already achieves quite the final performances. I mean, this means that you can imagine if you build a search engine, 250 queries can be submitted to it in a matter of minutes or even less. So the system will go to high performances very fast. Okay, for the conclusions, 2 approaches for keyword-based search over database have been proposed. Both approaches have no indexes on the database, so no a priori database content access is given by hypothesis. They're both based on hidden Markov models, and the hidden Markov model is used to match the keywords to database terms. And there is no bag of words approach because the semantic of both the ordering in the keywords and the database schema are preserved. And a training procedure has been developed that is called the least bit error training algorithm that is able to learn a top K instead of a single result. And the algorithm can be used in a semi-supervised incremental version, and it gives very effective performances. And also, the Kiri tool has been implemented to evaluate the approach and also to demonstrate to users how it works. That's it. These are the publications. Thanks for your attention.
Thank you very much.
Question? I've seen a few ideas coming from the signal processing communications area being applied to database search. Is something I didn't know. It doesn't matter. No, they are good, but they actually, it's an example, a very good example of a cross-fertilization. That is, hidden Markov models are commonly used in the area of signal processing.
Also the least bit error.
Also the expectation maximization, the least bit error, and so on. And they are mathematical tools for your optimization, but their initial use.
For signal
yes,
processing.
it's in the area of communications.
In our area, it's a lot of years.
So thanks again, and if there is not any question, okay. Actually, the second part of this afternoon was supposed to start at 4:30. So may I suggest to have a short break for a coffee or a tea? Okay. So we could start, say, at 4:10, 10 minutes, a quarter break, and then we start again. Thank you.